number 12 and lecture number 12, and we'll be doing some additional problem of Otto cycle and diesel cycle. Um, Otto cycle problem number 12.66, and that problem being in Bornak and Sontag, 7th edition. A gasoline engine has a volumetric compression ratio of 8, and then before compression it has got the temperature of 280 Kelvin and 85 kilopascal. The combustion generates a peak pressure of 6,500 kilopascal. Find the peak temperature, the energy added by the combustion process, and the exhaust temperature. So before we go into the solving the question, let's check like what's been given and which state been given over here. So we have got the volumetric compression ratio, which is V1 by V2, and that is equal to 8. So, and that is R, which is equal to V1 by V2 equal to 8 over here. Before compression, it has got the property of 280 Kelvin and 85 kilopascal. So the compression starts at state number 1. So we have got at state 1, we have got 280 Kelvin and 85 kilopascal. The combustion generate a peak pressure of 6,500 kilopascal. So the peak pressure after the combustion, that is at state number 3, and that is been given as 6,500 kilopascal. So the pressure P3 is equal to 6,500 kilopascal. And we need to find the peak temperature, which is actually T3, and we need to find the energy added by the combustion process, and that's been from state number 2 to 3, and the exhaust temperature, which is state number 4, and we need to find the temperature at T4. So before again going to the solving this Otto cycle, just rewind the lecture number 12a, and which we have been in which we have discussed different processes. So from state number 1 to 2, we have got adiabatic compression or reversible adiabatic compression, which is also known as the isentropic compression. From state number 2 to 3, we have got constant volume heat addition. From state number 3 to 4, we have got adiabatic expansion or isentropic expansion, we call it. From 4 to 1, we have got the constant volume heat addition. So going from state number finding the peak temperature, which is state number 3, we need to go from state number 2 as well. So at state number 2, the property would be from state number 1 and 2, and that is adiabatic compression. So for the adiabatic process, remember from lecture number 12a as well. So we have got the process, let's say from adiabatic compression P1 to 2. So we have got P1 V1 raised to power k would be equal to P2 V2 raised to power k. For value of k for the air, we would be taking as 1.4. So P1 V1 raised to power k is equal to P2 V2 raised to power k, and that mean like P2 would be equal to P1 V1 by V2 raised to power k, where V1 by V2 is already the compression ratio, and that's been given as 8. For the temperature, we can write the equation which was Tv raised to power k is equal to constant, Tv raised to power k minus 1 is equal to constant. That also mean like T1 V1 raised to power k minus 1 would be equal to T2 V2 raised to power k minus 1. So from that equation, we can say like T2 would be equal to T1 V1 by V2 raised to power k minus 1. So for the pressure, if I'm doing it, so we have already got the pressure P1, which is 85 kilopascal. V1 by V2 is equal to V1 by V2 is equal to R, which is equal to 8 over here. We have got the K value 1.4, just putting the value, and we have got the pressure P2, which would be equal to 1562 kilopascal. For temperature T2, just putting the value again, and we have got the temperature T1, which is equal to 280 Kelvin. V1 by V2 is 8, K minus 1 would be equal to 0.4, putting the value, and we have got the temperature T2, which is equal to 643.3 Kelvin. Now moving towards the now we have got the moving towards the state number 3, finding the peak temperature now. So the process from 2 to 3, It's constant volume process. So using the ideal gas equation, which is PV raised to PV by T is constant. So from ideal gas equation, if already even the volume is constant from T to from 2 to 3, then we have got the process P by T is equal to constant. So having said that, from 2 to 3 we can write like P2 by T2 would be equal to T3 by T3. So in this equation, we know the temperature, we know the pressure P2, which have already been find out now, over here. We know the temperature T2 over here, and we know the temperature P3, which been given over here, which is equal to 6,500 kilopascal. Yes, if it has not been given, then we must be using some other kind of equation. So we have got already these three unknowns, so we can find the temperature T3, which is equal to T2 P3 by P2. 643.3 is over here, 65 by 156, 1562, and we have got the temperature, which is equal to 2677 Kelvin. Now for the heat transfer from 2 to 3, as we have said, like the process is constant volume process. So in a constant volume process, as discussed in lecture number 12a, so Q would be equal to change in internal energy plus work done, remembering the first law of thermodynamics. And for the constant volume process, work done would be equal to 0. So we have got the heat transfer, which is equal to U. So for the ideal gas heat transfer, so Q would be equal to change in internal energy, and internal energy, we have got the equation which is equal to CV delta over. So for the process from 2 to 3, so Q from 2 to 3 would be equal to CV T3 minus T2, and that means like, so Q would be equal to CV T3 minus T2. So CV for the air using the table would be equal to 0.717. T3 is already been found out, and that is 2677, and T2 is already here, and that is 643.3. So we have got the heat transfer, which is equal to 1458 kilojoule per kg. Now for the and that's what actually been required, like the peak temperature and the energy added to the combustion process. Now for the exhaust temperature, which is equal to T4. So for T4, again the process is constant volume heat rejection. So constant volume heat rejection, and no, that from that process we cannot find, as we do not. Yes, we can find out anyway. So we have already got temperature T1. We have already got pressure P1. So we can say like P1 by T1 would be equal to P4 by T4. Sorry for that. Yes, we do not know the pressure P4 over here. So yes, we can use the other equation, or we can come from the state number 3 to 4. So state number 3 to 4 is adiabatic expansion. So for the adiabatic expansion, again, we can write the equation in terms of volume, and that is equal to T3 by, T4 by T3 would be equal to V3 by V4 gamma or K minus 1 over here. So for the temperature T4, you can say like T4 would be equal to T3 V3 by V4, and that is K minus 1. V3 is already equal to V2, as the volume is constant. V1 is already equal to V4, so that you can write the equation. This is T3 and V2 by V1. Why we are writing in terms of V2 and V1? Because the ratio V1 by V2 is already given, and that is 8. So we have got V2 by V1, that would be 1 over 8 then. So just putting the value, and you can find the equation, which is T4 would be equal to T3 by 8 raised to power 0.4, and we can get the temperature, which is 1165. Moving towards the next question, which is problem number 12.67, same Bonac and Sontag book. um, 7th edition. To approximate the actual spark ignition engine, consider the A standard Otto cycle that has got the heat addition of 1800 kilojoule per kg of the air, the compression ratio of 7, and the pressure and temperature at the beginning of the compression process is 90 kilopascal and 10 degrees centigrade. Assuming the constant specific heat Cv, Cp, and R would be constant, taken as constant, with the value from table A5, determine the maximum temperature and pressure of the cycle, the thermal efficiency, and the mean effective pressure. So looking again towards the same, this question, it more or less similar to the question we have solved in lecture number 12b, with different values now, obviously. So we need to find the maximum pressure and the temperature of the cycle. So as discussed just right now, the maximum temperature and pressure would be as state number 3. So we have got the maximum pressure P3 and the maximum temperature, which is actually equal to T3. The thermal efficiency, which we can find it from later on, and the mean effective pressure. So going from starting from the state number 1 and obviously going towards the state number 3. So let's say uh, starting from 1, we can find the state number 2 and obviously proceed towards the state number 3. So state number from 1 to 2, we have got the adiabatic compression as discussed. So for the adiabatic compression, again P2 would be equal to P1 V1 by V2 raised to power A. P1 is 90 kilopascal over here. Um, volume V1 by V2, or which is compression ratio, is that is over here, which is 7. So 90 into 7 raised to power 1.4, we can say like the pressure P2 would be equal to 1372 kilopascal. For temperature T2, we can use the same equation we have just set in the previous question as well. T2 would be equal to T1 V1 by V2 raised to power K minus 1. T1 is 10 degrees centigrade, converting into the absolute scale. Make sure like whenever you are using the ideal gas equation, your temperature must be in the absolute one. So T1 is 10 degrees centigrade, 283.2 Kelvin, and the volumetric ratio, compression ratio is V1 by V2, which is equal to 7. Just putting the value, and you can get the temperature of 616.6 Kelvin. So once we have got the temperature P2 and T2, we can proceed to the point 3, which is the pressure P3 and T3. Now the temperature T3, we did find out the temperature T3 using the equation that was for the constant volume. That was, if we can say like P by T was constant. So, but now over here, uh, the pressure P3 is not being given, so that's why we cannot use the temperature, this equation, which was over here already. So you can use the another equation, that mean like using the equation of the heat transfer. So equation of the heat transfer from 2 to 3 for the constant volume process is equal to CV T3 minus T2. So we have been given the heat transfer, which is equal to 1800 kilojoule per kg. CV for the air is 0.717. The temperature T3 we need to find out, and obviously the T2 is already been found out, which is 616.6. So just arranging this equation up there, so you can find the T3, which is equal to T2 plus QH, which is from 2 to 3, divided by CV, which is 0.717. Putting the value, you can find the temperature, peak temperature, which is equal to 3127 Kelvin. Once you have got the temperature, then this equation can be used, which is P3 by T3 is equal to P2 by T2. In this equation, we have got T3 now, we have got P2, we have got T2, and just putting the value, you can find the pressure, which is 6958 kilopascal. Moving towards the finding the thermal efficiency, you can find the thermal efficiency using the volumetric the efficiency equation, which we derived in the lecture number 12a as well. but also you can simply find the thermal efficiency using the Carnot, as this is the a standard cycle. So thermal efficiency would be 1 minus T1 by T2, and that mean T1 is already there, T2 is already there, so you can find the thermal efficiency, which is 0.541 or 54.1. The network would be thermal efficiency multiplied by the heat transfer, or efficiency is work divided by heat. Anyway, so the work network would be efficiency multiplied by the heat transfer, which is 0.54 for 1 multiplied by 1800, and you can find the network of the cycle as 973.8 kilojoule per kg. For the mean effective pressure is the network divided by the swept volume. So if you can say like the network is already there, but the volume, which is V1 minus V2, is not there. Yes, we have got the volumetric ratio, or the sorry, the compression ratio, which is V1 by V2 is already there, which is equal to 7, but individual volume is not there. Using the ideal gas equation, which is PV ratio PV by T is equal to constant, as I said like earlier as well. So that is like PV by T is equal to constant, and that is equal to R. So P1 V1 divided by T1 is equal to R. R for the air is 0.287. So we have already got P1, we have already got T1. You can find volume V1 easily, and this is 0.9029 cubic meter per kg. Now for the volume V2, yes, we can simply use this equation. We have already got to volume V1. Just putting the value, and you can find the volume V2. Putting that volume V1 and V2 in this equation, you can find the mean effective pressure, which is equal to 1258 kilopascal.